the fun we had, on the calculation, is where we're going to end up with the. How was the phase one? Good, easy. Did you get any physical meaning out of it? Just I know you did simulate it, you did some graph. Did you guys get any physical meaning out of it? What you were doing? Because one person asked me, I don't know, not to kind of pick on anybody, but one person told me how I can control the fundamental harmonics. You cannot. This is 6 step, right? The DC was supposedly is fixed. And you have a 6 step. There is no way you can control the first fundamental. Whatever it is, how much was it? I think it was 4 VDC divided by pi, something like that, right? That was the fundamental harmonic. That's it. There is no control on it. But if you have a sine PW, you have a MA. You can change the MA, and you can control the fundamental, right? So let me see where I finish. And one of you guys has a good hand writing notes. I'm going to give you extra 5 points, if I can get a copy of that, One of you guys is writing it clear and nice, 5 extra points for that, Copy. I'm not going to take your note. I'm going to take it and make a copy and give it back.
The end of the course?
End of the course, yes. I'm going to take it. Everybody has this sheet for today. Today, I'm going to go, let's see, we're going to be here, I think, until 7, something like that. I don't know when I'm going to give you a break. Let's start, to see. Do you want one? Yeah. Another one. And we should have another one, another sheet. I'm not sure where that. The rest. Oh, you need to see. Everybody has 2 sheets? So everybody should have 2 sheets. Okay. But this is toward the end of the class, not for now. If you remember what we did, we said we have an inverter, right? This is what we did, inverter. VDC, and we had a RL. You don't have to write it, you have it already. And you had a, I'm not sure what you call them, but I call this one EA, EB, EC. I put this one RL, IA, IB, IC. Then call this one VA, VB, VC. See that? VA, VB, VC. We did all the DQ transformation and all those kinds of things. My intention is to come up with the DQ equivalent of this system. And we will use it before the block diagram. They're very complicated, Tonight I'm going to give you homework 3. Homework 2 is ready. I'm going to give you the homework 2. And phase 2 of the project also is almost ready. I'm going to add the one I'm going to give end of the class to that, a little bit more than what we had last time. Most probably 99%, I'm going to give you phase 1, phase 2, and the homework number 2 tonight, And homework will be due until the next Thursday, next Thursday. So I think we got to this equation, if I'm correct, we got to this equation. EDQO was equal to RIDQO plus L. These are matrix, right? These are matrix. This is the 3 by 3 matrix. This is RRR. L, right? You have those things. L d over dt IDQO plus, I think what we had was L C d over dt. I should have called this transformation what says T instead of C. I should have called it T because C you may think it is the capacitor. This is not capacitor, it's the transformation matrix we have. C minus IDQO, right? I think this is where we finished last time, right? Am I right? Now, let's calculate this term. The rest they're clear. Let's calculate this term. How much is this term? We start with C minus. So we know C minus is 3 over 2 C transpose, right? Oh, sorry. So C minus is a C over 2 C transpose. And what was C? C was, I think it was it 2 over 3? I think, I'm not sure, was it 3 over 2 or 1 over 2? You had the cosine theta, right? Cosine theta minus 120, cosine theta plus 120, right? This one was sine, let me, this is what we had for C, I think. I'm just going to double check with it. 2 over 3 over 3 over. Let me make sure.
Yeah, it's true.
2 over 3?
Yeah.
Okay. We'll just calculate that. Yes, 2 over 3. Now, what is C transpose? You keep this one here. Just this one is going to come here. This one is going to come here. This one is going to come here, right? Now, when you want to you time this one, let's calculate the C minus. So C minus is going to be 3 over 2 times this matrix transpose, right? It's going to be 2 over 3 transpose of 2. So 3 over 2 times 2 over 3 gone, right? So this part they're going to get canceled, right? So it's going to be C transpose. Not C transpose, this part transpose, right? It's going to be cosine theta minus 120, cosine theta minus 120, and the same thing here. Sine theta minus 120, sine theta plus 120. And 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. Is it correct?
Why are 3 over 2 and our 2 over 3, so does that completely go away?
Yes, see, what is the C transpose?
Our C inverse multiplied by our C.
Let's put it this way. Let's put it this way. I do twist it. This is the C transpose, right? Yes. Is this C transpose? Yeah. Right? So 3 over 2 times that matrix. 3 over 2 will cancel 2 over 3, right?
Yeah.
Yes. Right? So I don't want to write it again. So basically, if I time this one by 3 over 2 is going to be C minus. So this is C minus. Right? Right? Looks like you didn't get it here, right? Because looking at it kind of strange. This is the 2 over 3, right?
Yeah.
So what is, I don't want to write everything again. C minus is 2 over 3 times C transpose times 2 over 3 times this matrix, right? This is 1, right? Because I'm saying, okay, raise this one and make this one minus, right? If you didn't get it, you're going to have to work on it yourself. So, now, theta is omega t, right? Theta is omega t, right? Basically, omega t, if you're going to look at it, plus delta. Delta is I said where these angles they are, right? We said this is A, B, C, for example, and this is a D, this is a Q, right? Before I start to write, there is a little, this one maybe will be like a delta 0. But as soon as this one happens, this one is going to start to rotate with omega t, right? How much is the theta? Theta is going to be omega t, sorry, with omega. Theta is going to be omega t plus delta 0, right? You have a car, this is your reference, 0. You park your car here, right? So you come back, you sit in your car, and you start to drive. What is the x? It's going to be x0, whatever you have, right? 10 meter, 20 meter, 1 kilometer, whatever it was, right? Plus vt, if you go with a constant speed, right? speed times the time, right? The same thing here. This is for an angular system. So how much is the d over dt c minus, this part? How much is this part? D over dt c minus is going to be omega time. What's the derivation of cosine of omega t? It was minus sign, right? Derivation of cosine was minus sign. Yeah, I think it was the second probably. And what is the difference? So why do I have omega here? Because cosine of omega t, the derivation is minus omega sine of omega t. Omega t I just replaced with theta, right? And here is going to be cosine theta minus 120, and cosine theta plus 120. And here, 0, 0, right? So we calculated d over dt c minus. Now, c times this. So c times d over dt c minus is going to be, we have c here, 2 over 3 cosine theta sine theta 1 over the square root of 2 cosine theta minus 120 cosine theta sine theta minus 120 1 over the square root of 2 cosine theta plus 120 sine theta plus 120. We do these things only once. Never ever look back to these things anymore. Just to let you know, and I don't want to write the equation right away to see what, because it will be always questioning your mind why these things happen. How did we get here? You know? So times that. I'm not going to write it here. Just leave it. Right? If you do this one, I'm going to give you a cheat sheet. You know, I'm going to upload this thing on the website tonight. I'm going to upload some documents tonight on the website. Here, they call it, I cannot pronounce this word very well. Trigonometric, relations. For example, this one times this one is going to be cosine sine, cosine sine, cosine sine. This one is going to be 0. If you do this calculation, you're going to get to this one. I'll give you this cheat sheet and practice this one. Make sure what I'm writing here is correct. Go double check it to make sure this is correct. If you do all these calculations, you're going to get to this one. It's going to be this matrix times this. Because this is 2 over 3 and this is omega. Just put them here. It's going to be 2 over 3 omega. See, omega is here, right? In constant, right? And you have 2 over 3, I put all of them here. 2 over 3 omega times, see, these two matrices look really bad. Right? But if you time it, you're going to get to this equation. You're going to get to this one. 0, 3 over 2, it's going to be pretty simple. 0 minus 3 over 2, 0, 0, 0, 0, 0. Those two big matrices, if you time it together, is going to end up that. Now, let's time this 2 over 3 here, and omega is going to be 0 omega 0 minus omega 0, 0, 0, 0, 0. So this is a C d over dt c minus, is that matrix. Now, I have all the elements. I'm going to rewrite them here. I'm going to put it in the matrix form. I start from here. Let's start with that equation. EDQO is going to be ED, EQ, EO, right? Is equal to. We have a RIDQO is going to be R00R0000R times IDQO is going to be IDIQIO. Right? Now, plus L is a matrix, plus L, oh, sorry. It's going to be L000L000L times d over dt ID, d over dt IQ, d over dt IO. Right? Now, the next one is this one, right? L, wait, what is L? I have it here again, plus L000L000L times what? C d over dt C minus, which is that, right? Times this one. It's going to be 0 omega 0 0 no, minus omega 0 0 0 0 0 times, I'm going to put it here. This is a what was that? That was C d over dt C minus. This is what we have here. And yes, ID, IQ, IO, plus the last one is VD, VQ, VO. Now let me just take it out from the matrix form. I don't care about the O, to be honest, because this is a balanced system. I don't care about O. So if I rewrite the equation, it's going to be like this. It's going to be ED is going to be RID plus LDID over DT plus this one, this one times this. You do this one, it's going to be plus L omega IQ if you times this one plus BD. And EQ is going to be the same thing, RIQ plus LDIQ over DT minus, this one is going to be minus L omega ID plus DQ, and EO is going to be RIO plus DIO over DT plus DO. These are those metrics in the just like. So, as I say, I don't care about the O circuit, but I'm going to draw it here for only for one time. I'm going to build a circuit based on this equation. So you know there's a circuit for the ABC system. It's like this, right? This circuit you have in the ABC system, right? I want to know what it is going to look like here. Look at here. If we are going to build the circuit here, just remember, these are the inverter output voltage, right? These are the inverter output voltage. I'm going to use this one too. So it's going to be like this. Say this is a VD, I put a DC value. going to be a constant number from now on. This one is going to be a constant number. This is R, and this is L, and this one is plus. This is L omega I. This is the equivalent of that circuit, ABC in the D axis. Q axis is going to be like this. And the O is going to be like this. O is simple. VO is 0, right? It's a balanced system. VO is 0. These are the three equivalent circuits of that ABC system in the DQ frame. Look at here. This is DC circuit. It is not AC anymore. Think about it. This is the AC circuit. This is what I said. We got rid of the frequency. We are not going like this. We don't have to follow this one anymore. We are going to only follow the peak value of this AC voltage or RMS value of that AC voltage. This is the advantage of the DQ. The frequency is gone, right? But there is a problem here. Let's look at it. This is a D circuit, right? And remember, we said we can control the reactive power with ID, right? And we can control the active power with the IQ, right? But look at here. If somehow something here is changing, it's going to affect IQ. See, let's put it this way. If I want to control my P, right, active power, I have to change my IQ, right? If I change my IQ here, right, this term here is going to change. Or if I want to control my reactive power, I'll change my Q value, which means ID value is going to affect this one. Basically, these two, they are coupled. There is a coupling term. When you take this one, this way, it's going to a little bit move that one. It's going to get stable at the end. But they are not independent from each other. They are not decoupled from each other. So I want to know how I want to work on that one, how I can make these two decoupled. When I change the P value, which means I'm changing IQ here, it doesn't affect my circuit here. When I change my ID value, it doesn't affect my Q axis. So I want to get rid of that term in this system. Keep this one in mind. Okay. So
what is L omega IQ in the system?
one is this one is L omega IQ. This one is L omega IQ.
What does it basically mean?
See, D axis is kind of coupled with the Q axis. Q axis is coupled with that. I don't like it. I want to be able to control my P, which is IQ, without affecting my Q axis, my D axis, because it's going to change a little bit of the reactive power. You're going to see all I'm talking about. Maybe in 3 weeks you're going to see all I'm talking about. When you do the ID IQ control, you can see when you change the ID value, you can see it's going to start to change a little bit. Even when we decouple it, it's not going to be perfectly decoupled. This is the math we are putting there, but in reality it's a little bit different. But we minimize that effect. We try to minimize that effect. When you change your P value, it doesn't affect your Q value, and when you change your Q value, it doesn't affect your P value. Active and reactive power, I'm talking. Not P. Questions?
Like in a physical system, what L omega IQ represent?
This is
Just
completely math. This is a completely math. There is not a real circuit like this. This is completely math, guys. Real circuit is here. See how many matrices things I put here to get there? This is a real circuit. This is what you have in reality. That one is a math concept. What was the advantage of that one over this one? Look at here. How this voltage looks like. VA. It's like this, right? How this one looks like? Here. It's like this, right? It's like this, right? That's the advantage of this one. When you had a circuit theory, which one was easier to deal with? DC circuits or the AC circuits? DC circuit was easy to deal with, right? So the calculation was much more straightforward. You didn't have omega term, you didn't have those kind of things. You go, you calculate it. You have transient, because of L or C something in your circuit. But if it is a steady state, you can say L is short circuit, capacitor is open circuit, is just like a resistive loop. You deal with that like that, right? Now, we have this equation. I want to get the block diagram for this. I'm going to get the block diagram for this system because I'm going to use it later. Later on, when I put my full control system together, this is my plan. This is my real system. Let's see how we can put this one in control blocks. How we can put this one in control blocks. Before putting this one in the control blocks, I'm going to use this one. Get a little bit more work more in this one. Just I want to put it in the state equation, state space equation. You know that, right? A state space equation is that x dot is equal to ax plus bu. How many of you have seen this one? Just one? You have control, right? You haven't seen this one? X dot equal to ax plus bu. X dot, for example, x is a matrix of x1, x2, x3, for example. So basically, x dot is going to be x1 dot, x2 dot, x3 dot equal to a matrix times x1, x2, x3 plus b, again is another matrix, times your input, I don't know, v1, v2, whatever. You have seen this one, this is circuit theory. When you have a capacitor and inductors, have you ever wrote the equation, matrix form of equation for those one? This is the same. This is a capacitor. For every inductor, I is the x, and for capacitor, v is the x. Because they call them a state variable. They call them the state variable. For in current of inductor and voltage of capacitor, they are a state variable. They call this one a state variable. What is the state variable? For example, in a circuit, you have two capacitor, one inductor, and they don't create loop or I don't know some of the things. If you know those three values, for example, you have two capacitor, one inductor. If you know the voltage of the capacitor and the current of the inductor, you can find anything you want. I'm going to put this one in the state variable form. I'm going to put this one in the state. So basically, if you look at here, I said x dot is equal to something. Means the one, I'm going to use this one. The one, the derivative of IQID is going to stay on one side, the rest are going on the other side, right? So basically, from the first two equations, I can put it this way. I can say dID over dt is equal to, and dIQ over dt is equal to. Somebody tell me what's the dID over dt? Right? The rest is going to go here, right? It's going to be minus RID. Minus, correct me if I'm wrong, minus RID. Right? Minus L omega IQ. Plus VD plus E. Is it correct?
Minus.
Is this one correct? Minus, you said minus VD. Is it correct? That's plus VD over there. Is it correct?
No.
Just I want to check it. I think you guys will check this, but you do need to know the state space variable, right? When it comes to this side, this one is going to be minus, right? And one more mistake here. Which one is wrong?
Yes.
Which one?
The whole
All
thing.
of them.
The whole right side.
Not all. This one. Or is the minus L omega Q, right? Is it minus or plus? So it's plus. So it's from your minus. I got that's the other one. This is minus. No, the rest are correct. Minus VD plus VD, right?
Divide by L.
Divided by L. You're right. Let's put one by one. How about here? start with the term ID. What's that?
Minus omega
Plus plus L omega ID over L, right?
yes.
And the next one I'm going to put IQ. Tell me what's the IQ then?
Minus R IQ over L
And the next one is going to be
VQ
VQ minus VQ over L plus EQ over L. Yeah, I said I don't care about the O version, you know. So just let's simplify this one. It's going to be like this. dID over dt is equal to minus R over L ID minus omega IQ plus 1 over L ED minus VD. And dIQ over dt, right, is equal to minus, not minus, plus omega ID minus R over L IQ plus 1 over L EQ minus DQ, right? I want to put it in a state space, you know. The reason I want to put it in a state space, you know, form, because if one day you get expert with MATLAB Simulink, it does solve this equation like this for you, you know. You don't have to even scratch your head. You just put a parameter and boom, it does solve it for you. You don't have to spend any time. So here, so basically you can say this is the state space. D over dt, ID, IQ, see this is the x dot. If you think about it, this is the x dot. What is x? X is ID, IQ, right? Right? X dot is going to be D over dt ID, D over dt IQ, right? You know, dot means derivation, right? Is a term we're using, an abbreviation we use here, right? Okay, equal to minus R over L minus omega, omega minus R over L ID IQ. Basically, this is the A, right? This is the X, right? X dot is equal to AX, now plus DU. DU is a little bit, you know, I'll put it this way. This is a state space, you know, 4 of this equation. Now I'm going to draw the circuit. No, I'm going to draw the control block diagram for this. Let's use this equation. See, what we are going to find out at the end, we are going to find IDIQ. This is what we are looking for, right? I'm going to put them here. Let's say I have the IDIQ. This is the ID. I have my answer. I found it. Just I put them here, right? Now let's see how we can get there. I'm going to go one block back. See, look at here. This one is going to come from here. This one is going to come from the IDIQ. It's going to be, if I have a ID, it's going to be times R over L. Right? It's going to be that term. I'm going to have omega IQ here. I'm going to have 1 over L ED minus VD. Right? So this, oh, okay, got it. If I have 1 over S here, this one is going to be ID. Is it correct? Look at here. What I did, I add all these things together, right? If I have ID, let's say I know how much is my ID, right? I time it by this term, R over L, right? I know how much is my IQ, I time it, I basically I should put it like this. This one is plus, this one is minus, and put it this way, right? I know my ID, I time it by this. I know my IQ, time it by this. And I bring this one all together. This one is what? dID over dt, right? If I take the integral of this one, 1 over s means the Laplace transform, right? It's going to be how much? ID. Let's put it there. Let's put it there. Because I want to make it look good, you know, that's my intention. Yes. No, I want to write nicely. That's my intention. Here I have to write this one. This is one of the projects I was working in general economics, just to let you know. This is not just the math here. We use it for real projects. Just I want to make it look good, you know, at the end. Let's put it this way. Bring this one a little bit down. This is the ID. And this is the IQ. Right? So I'm going to get the ID value times it by R over L. Or let's put it R here. I'll put the L in here. This is 1. Let's put this one here. This one comes with a negative sign. And the next one I need is going to be the next one I need is going to be I'm going to write and explain. What we need here? We need a RDID minus omega IQ. So this one also should be minus. Or not, keep this one down here. And plus ED. I'm going to put ED here. And minus V. Let's see if this one doesn't work. Let's see if it's correct or not. Basically what I did, I put the L here. I put the L here, so this one should be L omega, not omega. This one should be L omega. Let's see if this one is correct or not. I assume I know my IDIQ. They are known, right? I have. So if I want to make the one I put it over there is based on L is here. You know, the one I put it over there, L is here. Is the L dID over dt is minus RID minus omega L IQ ED minus VD. I'm saying if you time this one by L, is over there. So I should have a minus RID, right? Minus L omega IQ, right? Plus ED minus VD, right? So look at here, did I put it? I said plus ED minus VD, right? Minus RID, right? And minus L omega IQ. I divided everything here by L here. Just I divide by L, I put it here. And over S, right? I'm integrating of that, right? This one is going to be ID, right? So basically here, what do I have here? This is the L did over D. This is that equation over there, right? Go look at that equation over there, the top one. The top one, I'm going to write it here. The top one here is the L did over dt is equal to minus RID minus L omega IQ minus DD plus ED. I wrote it this way because I want to put it in a state space form. But look at this equation. This is exactly what I put here. ED, the last term, plus ED, right? Minus VD. I put the minus VD here, right? Minus RID. This is the ID, right? I'm timing it by R. Put it here with the minus left side. I have a minus L omega IQ. IQ times L omega minus, right? You add all of them together. If you divide it, it's going to be LDI over dt. If I want to find my ID, I should divide this one by L, right? It's going to give me dID over dt. And if I integral of that, it's going to be what? ID, right? Any question on this part? Clear? Let's do the same thing for the Q axis. So basically, I want to copy everything here exactly. First, let's bring that. I have to have for the ID, for IQ, I have to what? I have to have, where's IQ? I have to have a L omega ID, right? I have to have an L omega ID, right? So this is the ID, right? I bring the ID here, times by L omega, right? Times by L omega. And this one, with a plus sign, is going to come here. And we have an EQ plus, we have a VQ minus. Now what else we need? What else we need? So it's going to be R here. Why is it looking for this is the IQ. Right? Oh, we are missing one thing here. Again here, L omega ID, right? EQ minus VQ minus RIQ, right? What is this? This is the L DIQ over D, right? Divided by L is going to be DIQ over dt, right? 1 over S means you take an integral of this one, right? So it's going to be IQ. So if you're going to make it symmetrical, it should be here. So this is my circuit. This is my circuit, that circuit I have over there in the control block diagram form in the DQ system, right? I have this one now. What are these things? These are the output voltage of the inverter, right? What are these things? What are these things? These are the grid voltage in the DQ form, right? We had ABC. Now, if we select Q axis aligned with the phase A, remember? What is going to happen? This one is 0, and this one is how much? Is V, right? Is V. And what was V? V was the maximum phase voltage, right? Maximum phase voltage. We talked about those things, right? So this is for the circuit. Now I have my circuit here. Now I want to add the control part to this system. I wish I had another color. I can put it in different color. This is my circuit. This is my power circuit. And just to get an idea here, see, I cannot change VDQ. This is a grid voltage. I cannot change L. This is the inductor value. I cannot change R. This is the resistance value, right? The one I can change, I can control, is these two. These are the output voltage of the inverter, right? I can change, I can shift the phase, right? I can go back and forth with the phase. I can change the MA, it's going to change the magnitude, right? So now I'm going to select in my control system. Think about it. In reality, I cannot do anything, right? In the circuit, I can. But in my control system, I can do whatever I want. You know, this is math, right? I'm going to select these two such that cancel these two terms, right? Look at here. This is D axis, right? But it's getting tied to the Q axis through here, right? If somehow I can cut this one here, I can cut this one here. Think about it. If these two they are right here, there are two different independent circuits, right? If I could somehow erase these things, it's going to be RL circuit here, RL circuit here. You have some voltages coming here, some voltages coming here, and boom, right? If I can get rid of this part, they call it decoupled control. I cannot do it here. This is my circuit. But in my control system, I can do it. Let me see how we can do it in the control system. Now, let me simplify a little bit this one a little bit more. If, or let's be there. You know, at the end we say if, you know, the axes are aligned. Now, let's look at here. ED, I'm going to select it such that get rid of this term. Sorry, minus omega IQ. If ED and EQ, I want to have this ED-EQ. This is what I want to have. You know what I'm saying? I want to control my inverter to give me this ED-EQ. I'll tell you what I want. An inverter is going to go take care of it, you know, to give me that what I want, right? And I'm going to tell the inverter, hey inverter, I need this ED, this EQ. Go set whatever you should set to give me this ED, EQ. Now, look at here. If I want to get rid of if I want to get rid of this term, minus omega IQ, right? If this ED, think about it. If this ED, see there is a 1 over L also here, right? In this system, I have a minus omega IQ, right? Plus 1 over L ED. Just I'm going to write this term. This is the one I keep sharing about this, right? The rest I cannot control. VD, VQ, these are not under my control. This is a grid voltage. If I can select this ED to be IQ plus 1 over L, I want to have a term like this, L omega IQ plus, I call it X1, plus HE, plus something, X1, right? I want to select my ED this way. What's the advantage of this? What's the advantage of this? If we have I have 1 over L times L omega, right? It's going to be omega IQ It's gonna cancel this one, right? It's gonna get rid of this thing, right? So I select my ED to be L omega IQ. I don't know, should I put it X1 or LX1? Right now I put the X1 and I keep the distance here. I need to add L later, I'll be like. How about the EQ? Hmm? How about tell me? What should I select for EQ? I want to get rid of what?
L omega ID.
L omega ID, exactly. I'll tell you what's this X1, X2. Hmm? Yeah, you're right. Minus L omega ID. Minus L omega ID. You're right.
How to make sure x1 and x2 is not related to omega here?
We'll get there. Hold on. It's a little bit better. I'm gonna add the. I don't have any. Is this one different from this? I'm not sure. Nope. I'll put it this way. Right. And I assume I have an ideal inverter. It's gonna give me whatever I want. Right. Now, look at here. Look at here. This ED should go there, right? This ED should go there. So before this ED, I had an X1, they call it X1, plus how much? And ID is coming here. Just keep in mind this is the ID, right? Right? IQ, right? IQ, sorry, IQ. Keep this one here, just I put it a little small. Let's put this one here. How about this one? I think this one was negative, right? Negative L omega I, right? This is the control. Control circuit, control board, control processor, whatever. Now, let me first replace this one here in this equation. If I replace this one here, it's going to give me this one. dID over dIQ over dt over dt. If I replace EDEQ from here to here, what is going to happen? Let's put an L. So if I replace ED here with that value, what is going to happen? So this term is going to go away, right? It's going to be like this. I think I'm using one. Yes, I'm missing one. Here, I should put this one also. Right? Yeah. Plus VD. I want to get rid of F. I got to put one right there. So basically, there is one more here. What is this? It's going to be ED, is going to be, is it plus VD, right? Plus
But in that case, you're going to have 2 ED.
uh,
So in that case, you're going to have 2 ED, right?
What? Hold on. What did you say?
If you're trying to VD there, you just replace that in there.
Yeah, I just replace VD here. I'm gonna get rid of VDE2 also. I'm gonna get rid of all of this. I'm gonna get rid of this term and this term, right? Now, just I put it on that block there. That block number is gonna get really simple at the end. The one I'm putting over there. Initially, it's kind of big and complicated, but later on you can see it's really simple. It's gonna get really simple. Now, this is for control purposes because we are going to select the KPKI. Remember what I said in the last class? KPKI. You need to have a system to go plot the either bode plot or root locus or whatever you want to design the system to be critical damping, to have the fastest and the overshoot free system. That's what we are doing here. Let me finish this one and we'll talk about it because now we're right in the middle. So. If you replace these two, we select this one, replace it in this equation, this is decoupled system. You got here? dID over dt is minus RL over ID plus x1. x1 is an error from somewhere. There is no IQ anymore. ID is ID. They call it decoupled. See here? This term couples into the IQ, right? We made it 0. By selecting it down. This term will couple this Q axis to D, right? We got rid of that one, right? Now, x1 and x2, what are the x1 and x2? x1 and x2, they are, I don't know, let's put it PI. I mean PI, this is a PI controller. PI controller, block for the PI controller. We had two type of PI, right? We talked of KP plus KI over S, and then there's a KP parenthesis 1 plus 1 over tau S, right? Either way, you can just put the PI times ID star or ref, let's call it ref, minus ID, and this one is PI times, PI times IQ ref. These are the control rules. See, I have a controller here. So basically, look at here. I put a block L here. I put a block L here. Which we are going to get rid of it later. These two are coming here. Look at here. This is my ID ref. And I'm thinking how we're going to draw this. This is my ID ref coming here. Oh, I forgot PI. And I will have the same thing here. IQ ref. Positive. Now what I need this is the ID minus this is the IQ minus and this will come here. This one goes there. And IDIQ, your feedback. Here guys, look at here. ID coming here, IQ coming here. This is where you connect the control system to the power system. Right? this is the feedback in the system. ID feedback, right? IQ feedback. Okay. Now look at this one, we're going to simplify this one. Now we're going to get to the part you guys like. This is the control block diagram of this system. Is it clear?
No.
No? Which part is not clear? Tell me which part is not. Let's. Is this part clear? What we did here? This is a circuit, right? Power circuit. Was it clear here? Is it or not?
Yes, putting the resistor block. Okay, so there is an arrow pointing to the resistor block.
Yeah, this is the arrow is going here. Correct. Arrow is going here. Yes. And this is arrow going here. Arrow going here. This is the power circuit, right? Inverter is going to give me EDEQ. But how this inverter is going to give me EDEQ? See, this is the ideal inverter. What I put here is the ideal inverter. I'm going to go use the same circuit, put it in the PWM inverter. But first, we need to think about this one as ideal inverter. See, basically there is an ideal inverter here. If you think about it, you calculate EDEQ. You will tell the inverter, I want this much. So it's going to create exactly the same thing for you. You know what I'm saying? Like a unity, block. I want this much EDEQ. This inverter is going to give me the EDEQ, right? So that's the reason I didn't put the inverter here. This is the control circuit. This is the load, RL and the grid, right? But there's an inverter block here. I'm going to add that one later. That's the next block we're going to do. Okay, now. Should I simplify this one right now, or let's put the inverter block. Wait, with the inverter block together. We'll do it here, and after that.
Professor?
Yeah.
So we derive the control pattern based on the equation we use over here.
Yeah.
In this case, we use an integrator at the end. But if I rearrange this equation, I can use a differentiator as well.
Yeah. But you need to calculate. See, you need to calculate how you're going to
Undersize those, yes.
How you're going to do that.
Let's say we move everything to the left, just isolate ID, and then we get all the terms from there. In this case, we use differentiator. So,
But differentiator, we try to avoid differentiator in the control system is going to end up, is going to make the system very possible to unstable. It's going to make it unstable. But you can build it that way also, But let me put the block diagram of system with the inverter here, because this one doesn't have an inverter. I'm going to feed in the inverter here. I'm going to feed in the inverter here. So, and I don't care about this part for now. This is load, right? And let me go over here one more time. I wanted this much ID ref, I want this much IQ ref, right? Basically, it means how much P I want, how much IQ I want, right? Like the previous block diagram I drew out, right? We said, we should divide it by, 2/3V, something like that. We calculate that one, right? If you have a P ref and Q ref, anything ring in your mind, what I'm saying? Have a look at the previous block diagram we had for the DQ control. We said we have a P ref, Q ref coming, we had a block to calculate ID, IQ ref, right? I didn't put that part here because it's a repeat of that one, I started with this one. I have my ID ref value, I have my IQ ref value, I have my ID actual, I have my IQ actual, right? I take it to a PI controller, right here, a PI controller here, a PI controller here. I want to get rid of that coupling term. I'm going to add this term here. I'm going to subtract this term here. One of them should be negative, one should be positive. Let me see if I can make a mistake.
IQ LW.
Yeah, it gives one ED. This one should be positive. This one should be positive. Both of them cannot be negative. And I added this VDVQ to create my desired EDEQ. If my EDEQ is this much, right, it's going to end up an equation like this, right? This is what I like. This is a decoupled control. D axis doesn't have anything related to Q. Q axis doesn't have anything related to D, right? So basically, I build this part. If I have this EDEQ, I'm going to put it on my load, so my system should work, right? Now let me draw this circuit, this control diagram with the inverter in the system. So basically, we have ID ref, right? And we have ID. Let me put it here. ID, right? We have an IQ ref. This is the same block I'm putting over there. Plus minus IQ. Right? This is the first part that goes over. How I'm going to calculate my ID ref IQ ref? ID IQ. Somebody tell me. How? How? I'm going to calculate my ID IQ. C, I'm going to follow it with C. Right? A, B, C to D, Q, O, right? I use the matrix C. The only thing here, let's put it I, A, B, C to D, Q, O, and I should have a theta input, right? We need to have a theta here. We need to bring the IA, IB, IC, right? To this block. We sense it from the circuit and bring it here, right? Now I have my ID, IQ, I know my references, right? I'm going to build the rest of it. This L, I'm going to put it inside this PI. Why?
Just the constant.
Yeah, just constant, exactly. Let's say we go, is it Kp time plus 1 over tau s, right? This is what we say. So this one times another constant, just put this one, this is call it Kp, right? Or call it K prime P, another constant, you know what I'm saying? You don't have to put this one here. You can merge it to this block, you know what I'm saying? I put it here because I want to match those equations. But you can merge this block together and again call it PI. You know what I'm saying? You can call this one again a PI, right? Correct or not? Yes. So I'll put a PI here. I'll put a PI here. Now, we came up to here, right? We are here right now. I need to bring these two terms. So, now let's give it now. We need to put these two terms, right? This one we need to put it here.
Can we get rid of it?
How? No, we did not. We cannot. You cannot put it there. It's going to make your system slower. But this is the way I want you guys to implement it in your control system. Now I need one more term here. So this one is the plus L omega, this is the minus L omega, right? Look at it. This is the critical part here, look at it. This one is going to give me EDEQ, right? The one the inverter should generate, right? But before going to the inverter, I cannot put the ED, I'm talking about the real circuit now. Can I put the EDEQ to the inverter? No, I cannot. I have to come up with the MAMBMC, right? To say, okay, this is sine PWM, I cross it with a triangular waveform, send those switching function to the inverter to start to say do those kind of things, right? I need to build that part here. In this system, I assume my inverter is ideal. Whatever I want here, this is my math calculation from my control, right? this inverter is going to generate downward probability, right? But in reality, I have to go through the PWM things to build this voltage, right? Now, I have this EDEQ. First of all, you need to normalize it. What does it mean, normalize? How much, for example, if you have a 4 AD system, line voltage, how much this voltage is there? 300, 400, something like that, right? But think about it, in the control for my MA, how much is maximum MA? 1. So there is something here I need to normalize this thing before going there. So I divide EDEQ by VDC, remember? VDC over to what we had in the 3-phase converter. It was either VDC over to up or VDC over to negative, right? I'm normalizing it here. I'm dividing it by that voltage. Now this one is going to give me 2 signals, right? Right? This one is going to give me what? Sometimes I call it DA, DBDC, duty cycle, but usually we use it MA, ECM. And we said we should put another block here. What was this block? To make sure this is limited to plus minus 1. Let me fix it. This part is similar to what you had. Now I have a MA, MB, MC, right? What should I do next? What should I do next? Right? Right? You compare this control signal to the triangular waveform, right? And here you are going to have SA plus SA negative. You're going to have SB plus SB negative. SC plus SC negative. So this guys they're going to go where? Thursday I'm going to bring the inverter with the gate driver everything. Gate driver usually is part of the inverter in the hardware. Right? So now right? I'm going to use the feedback here. Right? IABC, right? You need to measure IABC, right? Right? And what else do we need to measure? DABC. Right? This one should come to this system also. This one is a tape also. Right? Because I have a VDBQ, right? It's coming from here. This is the feedback here. Look at here, I didn't put the VDBQ here, you know, what you should bring it. This system is the same system. But I put everything in the DQ. In this system, only the control part is in the DQ, right? The rest is the real circuit. The rest is the real circuit. See, this is the inverter. If you're going to look at it, from here to here is the inverter part. Over there, I didn't put it. Over there, I didn't put this part, right? I assume whatever is here, boom, is going to come here, right? Just I said, convert ED, EQ to ABC, right? But what I did over there, I said, okay, hey, I'm going to go convert this one back. Here, right? This is what I built. And I connected to this part. I'm going to use that one for control design. That one is a completely math system. This one is a math system. I'm going to use it for my control design. We're going to talk about that now. Let's take a little break and just talk about it.
Why do we normalize by VDC over 2 instead of the maximum of the fundamental?
Because if you look at it, you know, remember we had something like this, right? VDC over 2, VD minus VDC over 2. Right? Just divided by this one is going to be 1 and 9, right? Two projects you're going to do from here. You know what I'm saying? Not this, the control is not in the system. So we're going to go do this part, and I'm going to teach another method of the switching. It's called the space vector PW. That's the papers I gave you. I'm going to ask you to run both of them. But for the final project, for the phase 3, you will use a space vector. Instead of sine PWM, you do it in the phase 2, you learn how it is, and just, you know, instead of doing sine PWM, you say space vector. Now, we want to design this system, right? KPKI, over K and tau, right? K and tau, we need to select those numbers for this system, right? Let's forget this system. We're not going to work with that. We'll come back to it. Come back with what we have in the math system. Let's start to look at this. Look at here, just I'm going to simplify it. This is the one node, right? All these things, they are connected to this node, right? Plus VD is coming. Minus over, right? Plus L omega IQ minus L omega IQ. Right? See, let me tell you what you are doing. You know, when we are going to design the control system, I have an ID. This is what I want. I want to find the transfer function for those guys, they have a control system and they know about the body plot and root locus and those things. You need to have a transfer function for the system, you know. In a control system, you have this signal coming, you have, I think you call this one H, and this one is a G, H or G, bring it reverse or just let me look at it quickly and tell you. G and H. Is the G and is the H is the X. Is the Y. And is the feedback system. This is the control system. You know what I'm saying? You have this reference value here, for example, is the temperature, right? You want to control the temperature, but your feedback is going to be for example, let's say speed in the car. You want to control the speed of the car, right? You have to command the speed. You have to measure the speed, right? You know, you need to compare them together. So basically, your feedback is one, right? But in different systems, maybe you have a feedback system to do something else, right? It's not just exactly one to one. You know, it's, for example, you change the I don't know. For example, in this HV system, right? If you change the there's a temperature, you put the temperature, but basically it's a thermostat, right? You change that thermostat, right? And it's gonna go increase the temperature, or it's gonna reduce the ratio is not to one. This is the temperature. This is the potentiometer, right? It is a kind of feedback system in the middle. But in general, this is a control block diagram for a system. You have a signal, you have a G and H, and going forward, right? So this system is going to be equal to this. Let me say how, because some of you don't have it. If this is Y, how much is this one? YH, right? And how much is this one? Let's call this one X minus YH, right? X minus YH, right? How much is the Y? G times error, right? Y is equal to G times error. Error is this much, right? G times X minus YH, right? Just solve this equation, find the relation between X and Y. So it's going to be Y plus GHY is equal to GX, right? So basically, X over Y is going to be
G of 1 plus GH.
no, Y over X. Y over X, sorry. Y over X is going to be G over 1 plus GH, right? Basically, instead of having a feedback system, you could have a system like this. X coming, going to this block, which is a G over 1 plus GH, and this is a block, right? And they call this one transfer function of this system. Transfer function of this system. They will use this one, this transfer function, for control analysis, you know, for stability analysis. This is what they use. You know. Let's now do here what we are going to have. I'm going to go back to this block diagram, and I'm going to do it for example, D-axis. I'm going to plug it for D-axis. Q-axis is going to be exactly like D-axis. You know, no difference. Let's start to simplify this, right? As I say, look at this pole. VD is coming. Now just put them together. I have an ID out here. I have an ID ref in here. X and Y. X is ID ref. Y is ID, right? If I look at this system, this one, we cancel this one, right? This is the one node, right? Plus VD is coming, minus VD is coming, add together, 0, right? Plus L omega IQ is coming, minus L omega IQ, right? 1. This one gone. The same thing here. This one gone with this. Let me do it with a 2. This is a 3. This one is a 4. Right? So let me replot this system. It's going to be much easier. I'm going to put L inside this PR, right? So it's going to be like this. Basically, you don't need one. ID. So I'm going to have a PI here, right? I'm going to have a PI here. Right? This term and this term, they are gone, right? This term and this term, they are gone. So it's going to jump to here, right? It's going to be let me do this one this way now. It's easy to play. What you can see here? Feedback. No, feedback is there. What else?
Decoupled.
There is no IQ. Right? In this block diagram, there is no IQ. This is a system for ID. Right? There is no IQ anywhere. This is the independent control we are talking about. Let's put the same thing for this is minus, this is positive. So let's put the same thing for the IQ. The same thing exactly is going to be here. See, you have one block diagram for ID, one block diagram for IQ. This is the decoupled control. If you change something here, shouldn't affect it. Ideally, shouldn't affect that. If you change something here, ideally, it shouldn't affect. It does a little bit, but it's going to be better than the one you had initially. They were coupled together. Now, I want to design this control system here. See, I'm going to get into this one. I'm going to get into this system. Can I erase this one? The big one here. I'm going to do it only for one because they're a copy of each other, right? Just like explain for one of them, the other one. Basically, the PI value, whatever you select for this one, do the same thing here for this one. Now, if we simplify this block, look at here, just forget this part for now. Compare this one with that. Just get it up here, right? This is the G, this is the H, right? What is going to be G, which is R, sorry, is 1 over LS, right? Divided by 1 plus GH. Let me simplify this one. This one is going to be G, this is a G, right? 1 over LS over 1 plus GH, right? R over LS, right? Let's time the both, the numerator and derivative by LS. It's going to be 1 over R plus LS, right? So this circuit is going to be quadratic. I'm going to put my PI like this. KP times 1 over tau s. I like to use this one. Tau s. That one is going to be one block like this. See again, this one looks like this, right? What is G? G is this block times this block, right? How much is H? H is 1. So basically this system is going to be this. We call this one G. And H is equal to how much? 1 here, right? Now, control. How many of you know what the root locus? Root locus. How many of you have control? So, you have, did they teach you the root locus yet?
We're learning it like next week.
Next week, that's good. So, this is for 3 weeks later, 4 weeks later, you know. By that time, you know this one, you know. Now, this is your system. I want to design this system to be critical down. I'm going to leave it here for now. I'm not going to go there. The desire is to get the system critically damped. We talked about over damped, under damped, critical damping, right? So I'm going to leave this one here for now. The same thing you have for the Q axis. So basically, you should R and L, they are known. They are the circuit value, right? They are R, L, and there. So the things are not known. They are KP and tau, right? We want to design this system to be critically damped. Critically damped, you know what I'm saying? I want you in your report, you know, check with Arnold. I want you to go through everything to say, why did you select your KP this much, KP, tau this much? You may calculate that way, it doesn't end up perfectly well. You can tune it. But you will use this system to calculate your initial value for KP and tau, right? To design, this is a control design. They call it control design. There are not many engineers they can design good control system. Just to let you know, because to get this system, see how nice you put everything in the equation, simplify this one. For any power converter, you can come up with a mathematical model first, and after that you go through the control things. You know. So for example, we get to the block diagram like this and say, hey, design this system to be critical now. What do I mean by that? Hey, I have my ID ref like this. These are my command value, right? This is my command. You know what I'm saying? I can change it in my simulation with 10 amps, 20 amps, whatever, right? If we design the system critical down, it's going to be like this. Maybe you go a little bit overshoot, small overshoot here, but you get quickly, you get there. And again here, boom. See? This one is your command. This is your actual. This is a good control system. If you design the system bad, maybe you end up like this. Or you can have a little bit better design, but you get something like this. You know what I'm saying? It's a little bit better, right? And you go here, it's going to be like this. But see, look at how much you are far from the reference value. This is how good you can design your system. So here you could just say, design this system for critical damping, and the rest is yours for now. You guys think about what you should do. Okay? I want to design this system. You are done with the control part of this. I want to design this. I want to select KP and tau for the critical damping. Critical damping. Go think about it a little bit, you know, and maybe in 2 weeks I'll talk about it again a little bit more, you know. But for now, I'm going to leave it here. You guys do that. See here? This is my report. You know, believe I did all my stuff. This is the root locus. This is the body block for this the system I have. You know, I cannot give you this one because this one was paid in classified program. Usually you have this one. You know. And but these are the value here. This is the value here. These are the value we calculated. I use the control toolbox of the Simulink or MATLAB. Have you worked with the Simulink MATLAB? There's a control toolbox, right? Just go read a little bit about the root locus. Read a little bit about the body plot, because this thing is going to help you a lot to calculate this thing. You know, if you're going to do it yourself, it's going to be pain. You know, see, I did it over there with the not pain. You can do it, you know, if you want. They used to do it by hand, but now there's a good tool. Boom, boom, we put it there. You know, it's going to plug it over there. You can select those things. And Arnold did a very good report on this one last year. You know, try to use his time. You know, don't let him get sleep. You know, and let him use a little bit of his time for this part. You know, because he can help you very well and what you guys will need. You know, and if you ask question 1 night or 2 nights before the due date, block all the questions. That's what I'm telling you. Really, 2 days before the report, don't answer any more questions. You know what I'm saying? Because they should be done by that. Because last night I'm getting questions. You know, it's too late. You know what you were doing for the past 2-3 weeks. You know, now in the last minute you are asking questions. You know, what should I do this? What should I do that? You know, so this means you didn't work on it. So the last 2 days, not me, not Arno, we're not going to answer any question. So if you have any question, you have now until 4 weeks, minus 2, to ask all your questions from Arno. Okay? I'll give you the phase 2 tonight. Arno is going to post it on the website. Check the website. Homework 2 is coming. I may put some extra document on the website. There's one more thing to go over, before you wrap up, we want to do the last piece for the inverter, Let's go over it. Any question here? We need to control design here. I got it, I chewed it, I put it in your mouth. Now you need to swallow it, you know what I'm saying? This part is gonna be you, to design this, but you have the control system now. As from your control purpose, this is a piece of cake. From this point, this is a piece of cake. You have the model of the system. To model the system is the difficult part. But you have the mathematical, all those inverters, those crap, they end up in a single model. This is all you have. See? This is the advantage of modeling. You make it very simple. Now let's go to these pages. I call it switching technique. Let's go to the first page. I'm not going to explain exactly how did we get to that. Upload the paper, original paper. Is the paper is from Professor lec9 from the University of Minnesota, the one who has a book, He has a very simple paper about how we get there. But let's look at this page. We talked about this one. Look at it, it's a 3-phase inverter, right? Do you want me to put it on the, can you see, or I want to put it on the overhead? That's okay. See, here you have an inverter, right? And this is what I wrote before. I think here previously I called them capital N and small n. Here I call it G and N, right? Different notation. Just I said how to calculate VAG, VAN, VNG. This is better because it's the N and G. It's not NN, to get confused. And we went through this equation. We calculated all this equation here. And here, this is what we proved. How if we design PWM is going to be those equations. Remember, they're similar triangle. Here it's here. I'm going to upload this one also on the website. You will have it. And